are starting a unit on forces and motion. And our very first section is called Describing Motion. Important terms in this section will be motion, distance, displacement, speed, average speed, and reference point. This is the outline for your notes today. You are going to put the question at the tippy top of page 50. Yes, you should be skipping a single page from where we left off first semester. If this is your first semester with me, go ahead and just label page 1 as page 50 so you know which pages I'm talking about when I refer to them in class. You will then put the section title, Describing Motion. These are the main vocabulary words that we will go over. Do make sure that you have a place to draw this example diagram. Make sure that you write in the equation for average speed, which is distance over time. And then make sure that you have space for this section here, where we will create a little table with different types of speed. And that's enough of the music. Okay, here we go. So the question that is going to go at the top of page 50 is, are both distance and time important when describing motion? Then go ahead and put in section 1, describing motion, between there. Your first vocab term is motion. And as we discussed in class, motion occurs when an object changes position relative to a reference point. So the important term here is reference point. Remember, when we were talking about how can you tell that a car is moving, it's important to think about it. Can you see it changing position relative to other objects? If you're in the car, then you know that you are moving because you can see the objects going past you. So you can see things moving compared to where you are, which could be considered your reference point. Or maybe there's an object, a tree or something outside that you can use as a reference point, and you can see yourself coming closer and decreasing the distance between you and that tree, and that could be a reference point. So it's important to identify what the object is that is considered your reference point. Now, distance and displacement are two ways that we can describe how far, but distance refers to how far total an object has traveled, whereas displacement is the distance and direction that an object is from its starting point. If you are still working on getting this information down, go ahead and pause the video and you can finish copying it down, because I'm going to move on to show you an example picture. Here we go. Okay, so in this picture, what I want to show you is this is the first picture that you're going to be drawing, and what I want to show you is the distance versus displacement drawn in on this picture. So distance is going to be displayed by this red arrow on the picture, and then this yellow arrow shows displacement. So on the picture, we see this dotted line going around, and see how the dotted line just keeps going, but these yellow lines that represent displacement, they're showing the shortest line path from where you start to where you end. And that's what displacement is. So if we think about running around on this track, from here to here, we've gone about, let's say, 50 meters, because the whole track is 400 meters, so if that's 50, I'm just guesstimating here. And then if we get to about here, then that's 100 meters, and our distance and our displacement would actually be the same because we haven't started changing direction at all. But once direction starts changing here, see how the red dotted line is a little longer than this yellow line. This is the shortest line path. If you've ever heard the phrase "as the crow flies," that's if you could just fly over that way instead of going around, then that's what we're referring to. So then as we go all the way around here, we keep increasing our distance but our displacement is a little different. And then if we get all the way back over to, like, say here, then we're actually getting closer and closer to our starting point, and that displacement would end up getting smaller and smaller and smaller until you get all the way back here and your displacement is actually 0, but the distance that you've gone around the track is 400 meters. I've got a little clip here that I want to show you that demonstrates this again. I'm going to fast forward to
somewhere else,
where it actually starts talking.
To do this, we'll have to talk about a few new ideas.
Here we go. Distance versus displacement.
Distance tells us how much ground the ball has covered since it started moving. Notice how any movement of the ball adds to the distance. Displacement tells us how far the ball ends up compared to where it started from. Look at how when the ball gets closer to 0, displacement goes down, but distance is always increasing. So we can see that the distance tells us how far we have traveled, but gives us no information on where the ball is at any time, while displacement tells us where the ball is, but on its own doesn't tell us much about how far the ball has really traveled in the past.
So one more time, what they're saying is distance tells you how far total the object has traveled, 18 meters, or 18 units, whatever units these might be, maybe centimeters. But it doesn't tell you where the object actually is relative to where it started. Displacement tells you that. Displacement tells you where the object is compared to where it started. Here, in this case, 0, because it's at the same place where it started. Now, as it went this direction, it goes all the way up to 6. So our displacement and distance were the same until the object started turning around. Then the distance continued to increase, but the displacement was decreasing. And it finally got back to the same position, and then as it went past that position, it actually started becoming negative. And we will frequently talk about motion on a number line like this because it makes it easy for us to describe forward versus backward, to say forward would be positive and backward would be negative, so that you can add all of those positions up and figure out where an object is. And we'll get some more practice with that as we go along. All right, now here's distance versus displacement. Again, this is the second picture that you're going to be drawing. And so this is the Kansas Speedway. Whoopsies, there we go. This is the Kansas Speedway, and at the Kansas Speedway, it has a distance, the track all the way around is a distance of 2.4 kilometers. And can you guys figure out how many meters that would be? Remember that 1 kilometer is 1,000 meters. So if 1 kilometer is 1,000 meters, then how many meters would this actually be? Well, the correct answer is 2,400 meters. So 1 lap around would be 2,400 meters, which is 2.4 times 1,000. And the displacement for 1 lap is 0 meters. But let's say that I only go around halfway. In that case, let's do half of a lap. In that case, my distance would be half the distance, so 1,200 meters. And then my displacement, well, looking at this, I have no idea what that distance would be. Let's go with 500 meters, maybe? I don't know. I'm just taking a wild guess here. Okay, that's really stupid. Okay, so maybe it's about 500 meters from this position straight across, from point to point. Straight across, that would be about 500 meters. I'm just guessing. Now, I don't just want to say 500 meters for displacement. I need to know, did I go 500 meters this direction, or that way, however. So let's imagine that this is that this direction is north up here. This is south, east, and west. So I would say that my displacement was actually 500 meters north. If I was talking about starting from this spot right here and going to this spot. Let me draw a little line just to show what I'm trying to say from here to here. That would be a distance all the way around of 1,200 meters, and the displacement would be 500 meters to the north. So I would need to actually state that. Let me put a little arrow end on there. From here to here. Okay. Next, let's talk about speed. So speed is the distance an object travels per unit of time, and or also known as the rate of change of position. So how quickly you're changing position is your speed. And then the equation for average speed is actually total distance, not just distance, but total distance over total time. So please make sure that you get these two terms written down and also this equation. Speed equals distance over time. Now, the last thing that you need to put on page 50 is this table right here. So we're going to have types of speed at the top. And then for the types of speed, you're going to have instantaneous, average, and constant. Then you're going to talk about a description and an example for each. Instantaneous speed is speed at any given point in time, so a specific moment. So think about if you're in a car and you look at the speedometer, right at that moment, whatever the speedometer is reading, that would be your instantaneous speed, and that can change moment to moment. Average speed is something that we calculate. It is total distance that you travel divided by the total time. So this is the equation for speed, distance over time, but we're talking about total distance over total time, not just the speed at one specific moment. So think about if you're taking a road trip or even just going from home to school. You're not always going at the same speed. Sometimes you're going slow, sometimes you're stopped, sometimes you're driving more quickly. So what the average speed does is it brings together all of those different speeds and it gives you an average for the entire journey. So it's going to be somewhere between being stopped and whatever your fastest speed was. So that's done by taking the total distance, so however many miles from your house to school, divided by the total time, maybe minutes or hours, that it takes for you to get to school. And you could find your average speed doing that. Now, constant speed refers to speed that does not vary. Vary meaning change. So like a variable is something that can change depending on the input information. So vary means to change. Now, putting your car on cruise control would be a situation where you would keep the speed constant. So that would be an example of constant speed. You put your car on cruise control so it automatically puts on a little bit more gas or a little less gas depending on if you're going uphill or downhill. So that would be constant speed. Now, the last thing that I want to just talk about briefly here is this idea of graphing motion. This is another way for us to describe motion, not using an equation, but actually we're going to apply that equation to a graph. So at the top of page 51, I'd actually like for you to go ahead and draw just a little graph. It doesn't have to be too big, but just a little graph like this, and I do want you to label it the way that I've done here. So distance in kilometers and time in hours. And the distance is on the y-axis, time is on the x-axis. So on the top of page 51, you're drawing this. Maybe, make it about like 2 inches by 2 inches. This doesn't have to be very big enough that you can label it. But also, can you please make sure that you write down, plot the distance on the y-axis, plot the distance on the y-axis, and the time on the x-axis. That's how this is always going to be for a distance time graph. That's what this is called. This is a distance time graph. And then I want you to write down the slope of the line on a distance time graph gives us the speed of the object. So what I mean by that is if we think about what the slope of this line would be, we would be saying we do slope by rise over run, and rise over run would be y2 minus y1 divided by x2 minus x1. So you may have heard slope is rise over run, or slope is y2 minus y1 over x2 minus x1. Both of those are the equation for slope. So the rise for this line here would be 10 kilometers. The run would be 10 hours. So 10 divided by 10 would be 1. So this would give us a slope of 1 kilometer per hour, because you'd have kilometers divided by hours. So that actually tells us the speed. That tells us how fast the object is going. Every hour, it can go 1 kilometer. Now, what about this spot right here? What would the rise be? Well, the rise would be 0, because this is staying at the same height. And the run is actually 2, because this is 10 hours and it goes to 12 hours. So that's a change in time of 2 hours. 0 divided by 2, or 0 divided by anything, is going to be 0. So the speed right here is 0 kilometers per hour. And then this part, well, you can see that the slope is the same as it was over here. So it's 1 kilometer per hour again. And so if you guys could draw this graph here, and then these two pieces of information on either side at the top of page 51, that'll be perfect. And then let's just do a quick summary of everything that we have learned. So we've got motion is an object changing position compared to a reference point. Distance is how far an object has traveled, and that's always a positive number. Displacement, though, is distance and direction, and that can actually be a negative number if you go backwards past where you started from. Speed is considered a change in position per unit of time, or the distance divided by time. Average speed is total distance over total time. And then when we're graphing, when we do a distance-time graph, we always do the distance on the y-axis, time on the x-axis, and slope. The slope of that line will give us the speed of the object. That's everything that you need for your first lesson on forces and motion, and I'll see you in class.